So today's lecture gonna be very simple, basically review of mathematics. Most of you know, some of you might be a little bit why we're doing this. We are gonna use the same level of math for the first few weeks. I would say the first half of the semester. And I want you to be very quick because we will solve class participation in small assignment in the classroom, and you should be very comfortable using that. All right. And then they will show up in your exam. Once we get to dynamic, it's a different level differential equation. So we will cover those as well. So you would know what I expect. All right. I have a cheat sheet that I use. You can have your cheat sheet also. As you know, I will allow, you might not need cheat sheet for exams. So you can start creating your cheat sheet from now, for exam 1. Cheat sheet, like you can put the equations in there, but it just have to be equation. You cannot just solve the problems. And you know, I check the cheat sheets. All right, so I'm going to introduce rigid body and configuration space. Some of you might know what they are, some might not. They are mostly just concept. We want to get it out of our way. Plus, I want you to be vigilant on learning things that you have learned before you forgot. This is a very good website. I think most of you have used, right? Does a better job than me explaining things. I learn things from them because the way that they explain is very visual. I'm a visual person. So I highly advise that go and check these videos, especially if some of those are not your strongest suit. All right. All right, what is a rigid body? Anyone? Yes. So you can flex it, right? So your bone, the bone itself is a rigid body. How about the tendon and muscle? They're not, right? So we only deal with rigid body. And the idea is, at least for this course, is introductory. We want to keep things simple. So when they don't flex, they don't become part of our dynamic and kinematic, right? So it's all matters is this thing is this long, this link is rigid, doesn't move. It's connected to the next link through a joint. So very simple, you only have 2 things to worry about. So the distance of 2 points on rigid body doesn't change, you can't bend it. Right, so mathematically, rigid body is the distance of 2 points doesn't change. But if you wanted to explain to someone, you say you can't bend it. All right. Now, robots consist of these. Now, when we say that, we are thinking robots that have some sort of limbs, right? And it's just a car, it's just one rigid body. But there could be multi-bodies, which you will see, and then we call them chains. Because links, rigid bodies are connected through joints to each other. You see that I'm repeating this a lot because I want you to be very well versed of explaining it. When you're analyzing a robot, you always get the schematic version, that's what we saw, so you don't get the actual robot. You should be able to identify what is what when you see it. All right. Everybody knows a Spot Mini. There are a lot more versions of them now. Some of them are very scary things that they can do. But, well, I don't want to misguide you. So equation that we will use would not directly apply to Spot if a Spot was to move, right? If it was in one place grounded, everything you learn will apply. As soon as it's mobile robot, you have extra set of equations to consider. All right. So you'll see that there are manipulators connected to, let's say, underwater robots. So the manipulator part is attached to a base that is the underwater robot. So all equations are different from the equation of the robot itself that's moving. So it's not totally useless what we are learning here. All right. Few fancy words or words that you will see a lot, and I want you to understand what they are. Configuration, we talked about that a little bit last class, right? You defined the joints, and then you saw that a robot that has 2 rotational joints, which we showed with what? The letter R, and the prismatic P. So if I tell you a robot that has 2R and 1P, that's not enough information to tell me that what is it configured, how, right? So you need to know what is at least the order. That's the least. Then you what is your next question? So I say RPR. What's your next question? You asked me about that to know the configuration of the robot. Now, limitation, but something else will come first. What is that? The direction of the z-axis. Remember, it could be because the direction of the z-axis defines which way they're rotating or moving. Once you have those two information, then you can say that now it moves. It only rotates 90 degree or 180 or 360. That's extra information that helps you with the next topic that you'll see. But configuration is like that, the specification of the position of any point, because once you know how they're connected, you exactly know the position at all points. Assuming you know the length of the link and the angle of each joint, then you know where the robot is at any time, right? That's what we do in kinematics. Who knows what's the state? So let's say you have a system, like you hear a lot, the state of the system or state variables. You have control, you probably remember. Anyone? I see someone is at this reading. So what domain we live in? What domain do we experience as humans? Time. Right? There are other domains, frequency, log pulse. We had very fun with that in control paths, right? But we experience things in time domain. So when you model a robot that moves, so the position and velocity changes, those happen in time domain, or at least you analyze it in time domain. Now, to know where the robot is at any time, future, present, past, you need to be able to follow something, to calculate something, right? So if my hand is right now here and you want to know to get here, how does my hand move at and will be at any second, you need to know how this joint moves, right? So if you knew that I'm gonna go 90 degree and then 35, if this was supposed to move, let's say another 25. If you had this variable, right, then you know where my hand will end up, also called end effector. So remember joint variable we talked about last class? So those joint variables are one of the states of this robot. So the position, right? There is one more set of states that will help you to know where the robot would be or at each time, what is that other state? What else defines the position? From what else you can tell where the position of the robot is? These are all from physics. Yes, speed, velocity. So we have the velocity because we said at any time you want to know where the robot is. It might go fast. So at 10 seconds, the robot that goes faster is in a different place than a robot that goes slow after 10 seconds. So the position and the speed become the state. If you know those two, you know exactly where this robot is at all times. It's a rigid body, so nothing will bend, right? And if you know the length of the link, all you have to do is the angles. You simulate that and you get the position. That's basically the modeling of active kinematics, right? So the position states were theta, let's say theta 1, theta 2, theta 3, right? So it's one of the variables. These are the position. What would be the velocity for these? So if the position is theta, what's the velocity? The change of rate of the position, this is theta dot, right? Theta dot 1, theta dot 2, theta 3. So these 6 becomes your states. We will call them state variable. Once you know the information about this, you know where they are. Do we need to know acceleration? No, because we can get it from the velocity. And after acceleration, we don't have anything in this 3D board, right? So for us, the first two are enough. If you have the acceleration, cool. You just have to repeated states, right? And you know that when you're calculating, you need the least amount of variable in the field. So That becomes a state. The state of space is all these possible. So all the possibilities this six variable can have that will impact the position of the robot. So the angles from 0 to 1 to 360, if that's how they move, and the velocity from really depend on what kind of actuator you're using. Yes.
If you don't need the acceleration,
You don't know how fast, you need to know the rate of change of position, right? If you want to calculate acceleration, then you have error. You can estimate, yes. You could estimate, you actually do that. But if you want to not estimate the actual value, then you need to have it. All right. There are other different states. Let's say that your system has pressure in it. You need to calculate the pressure at a given time. Then that becomes a state. Usually for dynamic, we only if you are satisfied if we have position and velocity. Then if you have temperature, if you have pressure, I don't know, if you're using a camera, then the resolution of the number of pixels you're reading, that also becomes a state. So I'm just talking about something that moves in 3D space. And the minimum, usually the minimum number of the state that we can solve a problem is what we're talking about. Yes. Good question. Configuration space, or we show you C space, is the space that contains all the possible configuration of that robot, right? So you have the variables, depending on how much these theta's move, you can have your system. Who knows what degree of freedom? Just raise your hand. What is degree of freedom? Who heard degree of freedom? Okay, good. I will show you how to calculate. Don't worry about it. When I have to ask the right question. So the minimum, again, that's another important word. The minimum number of real value coordinates needed to represent the configuration. So you remember about my elbow not bending the other way, right? So this joint only bends this way. What's the degree of freedom? Yes, 1, right? We have a bit of calculating that. If you're a mechanical engineer, you have done this. If you're not, don't worry about it, you're gonna do it. The only scratch the surface, really simple stuff. Again, we say 2D and 3D and with a magnitude. So we don't have fancy mechanical camshaft or anything. Very simple. So we will get to that. Now, robots workspace is what I was talking about. Now, every robot, even if you have two similar robots, but they have different actuation limits, their workspace will be different. Do you remember me trying to grab his pen and not reaching to it? Okay, but this robot actually. So the pen is in the workspace of this robot, but not this one. So this arm, one of this arm. Now, if you wanted to write the state space of this robot, so this is grounded. Moves here, and from top. This one also moves. And you write state space or the state variable, the Q vector that you wrote last class. What's the Q? First find the Q, then tell me what's the state space. You know that you can get it from the Q. Yes. So what is your state space? So theta 1, theta 2, theta 3. So this is good. I brought this on purpose because I want you also to be comfortable with visualizing 3D, right? So this is top view. They are simple, but when you're solving a bigger problem, they become important. This information are handy. So let's say I call this one theta 1. That's the shoulder, right? It moves here. So this is the base, but that's this first one. Then it's showing that's rotating, and then another one. So theta 1. theta 2, theta 3. And the theta space is, so I'm gonna show, they're usually in column. Theta 1, theta 2, theta 3, theta dot 1, theta dot 2, theta dot 3. Once you have this information, you know where the robot is. Some of you might have PTSD. Oh my God, all the dynamic and matrix and state variable and yes. You're using all of that. If you have done this before, it's going to be very useful for this class. Now, so you see that there is like those gray area. They are the possibilities that this robot can go. So if you look from top, this can move, right? And this also can move. So this was 1 theta, and this also can go here. So this can go all the way from here. And you see that this distance is longer. Why? Why is not a circle? Why this is not going on a circle as its workspace? Because it can tip down, right? So this can go all the way here, and then the second link. So, yes. So that last one actually says is yeah. Thank you. Yeah, that does not do that. It create a different robot. Because the rotation is in a different one. Thank you. That's why it has this weird shape. Now, as engineers, the first question when you were, if you wanted to design, what is it that robot needs to do? What's the problem? What's the robot to do? Needs to reach to some area and fit. So you draw this workspace. From here, you design backward. Once you have the layout, you can imagine then you solve equation and you plot it and show it actually did what you expected. Right? And you will do that as part of one of your coding assignments. So that's great. All right, so compare the different workspace and you see that RRP, A and B, very different workspace. And then you have RPP, PPP. These are very, these are all famous robots, so it's good to become familiar with their configuration. Degree of freedom. Any questions so far? I went kind of fast through it. I think most of you nodded when I was talking, so that tells me you understood. So don't nod if you don't understand. You all good? Sweet. All right. When we talk about degree of freedom of a rigid body, we are talking about an object that is suspended in 3D space. So that's our assumption, then we go from there. Now, for an airplane, how many degree of freedom you can see? How many ways it can move independent of the other direction? To represent where this thing is. So you add them together and say how many? 6, 3, and 3. So airplane can go forward. Well, assume you can start go sideways too. Okay. So forward, sideways, up and down for sure, right? And then you can roll, pitch, yaw. So heading, rolling, and pitch, which is the nose goes up and down. So 6 independent way of moving that can describe all the different configuration of positions where this plane could be. Same goes for underwater robot. Same goes for this. If I want to throw it up, you can rotate about 3 axes, right? And you can move along 3 axes. So you see that. So I put COVID and I said axes. So the first thing we need to identify is the axis. We are in 3D world. How many axes do you have? Octagonal. 3. You always have 3 of them, right? So we can go along any of these axes. So 3 maximum here. How many rotation could we have maximum? 3. Also 3. The 6 is the maximum number of one object suspended and moving. right? So for objects like that, that would be 6. Now for humans, if I just say, so so let's say another object, I'm using myself as an object. If I'm grounded, the only way that I can move, let's say I'm trying to look at things, I can rotate this up, down. Right? 3. So only around 3 axes. Now, if you are very talented, you can also do that. Because that's something else. But now if I add the whole body, now I can move, I can actually go forward, backwards, that becomes 6. So what's the difference between those two? Why at one situation, it was only 3 degrees of freedom and one was 6? Yes. So what did my body didn't do the first time around? So I was constrained, right? In a bit. So constrained, they have an impact on the number of degree of freedom, even for an object that had the potential of having 6 degrees of freedom. So those are important also when you are calculating degree of freedom. All right? How about this point? How many degrees of freedom? 4. Okay, that's a little bit too many. Who said 3? Okay, tell me why.
If you assume it's flat, translate that to line.
Yes. So, I'm gonna use my stuff, so I don't touch your stuff. See what I have. Phone, everybody has phone. So, this is the object on 2D space, right? I can go up, down, so right, left. If I go here, the combination of the 2, right? So I have 2 coordinates, X and Y. Now, you see there's like these 3 dots of cameras. This is the orientation, right? So there is one thing that's here. So that also will be different that because it's different, because if you said like X and Y, so this should have been similar to this. But now imagine a car on the road. So car goes straight, it doesn't go sideways, but it can turn, right? So you have that angle as well. So it will be the XY position of the car and the heading. So you can tell exactly all the position that car is in, so you can represent all of that. So if I wanted to write, this was 6 EOF. This is 3, this is 6, and this is 3 DOF. Now, think about the door. How many degrees of freedom the door has? 1. You can only, it's a hinge, right? You can only open, that's it. Unless you're hawk and then move the whole thing. And that's different because you broke your system. That's not the system anymore. It is also really important to understand your system. You remember in control, we talked about, first you have to know what your system then control it. Same here, you need to know what is your system. Now, say that I have a manipulator on a car that can go and do something, pick apples. So the car goes and pick other people's apples, right? Now, if you wanted to solve, the car is parked and you're picking apples, but even though the car is in the system, it's not moving, not part of the action that's happening. So you should be able to isolate the system. Really, really important. We talked about robot joints, but I wanted to give you like very clear examples of prismatic and rotation, and knowing that when we have joints, it gives the object, it gives the robot, I'm just going to call it robot, the freedom to move, right? You also could have constraint because the joint right now is providing constraint of going backward. So looking at your system, you need to know your freedom of the joint that provides. So, and then the constraint that your system is implying on your system. Once you have both of those, deduct them, you have degree of freedom. Now we have a really cool equation that we can put other things in it and give us degree of freedom. But if you think like I would say abstract, but not abstract, you actually know what it is. Like generally it's just freedom minus constraint is degree of freedom. Now, what's the degree of freedom of this we just saw? Now, this is a joint, right? So any joint that looks like that has 1 degree of freedom. Prismatic joints, so body one, body two, any sort of, so you have access, could be anything. They move on one direction along one axis, that's 1 degree of freedom, right? Do we have any prismatic joints in our body? Outside of our body? Rigid body, you're talking rigid body. So when I say degree of freedom, I'm talking about rigid body. I know what you're thinking from that. Do you have any rigid body? You You're on the record. All right, so you chain doesn't have prismatic one. It's called chain because so nine-player chains they only are comprised of revolution. All right. Good, you're all great. That never came up. Adam, you're special. All right. Okay, so that was basically all the fun part of today's class. Yes.
So I have to wonder, is there a reason we don't differentiate, say you have a joint which can have one movement, but a joint like shoulder to ball joint, which can have multiple directions? Yeah.
Very good question. Does anybody want to, okay, let's have, I'm going to repeat your question and see if I was wrong. So is there any distinction between like, so when you're talking about joints, elbow that has one, so it's one R joints, right? Then your shoulder has more degree of freedom. So 3, mine has 3, I'm very flexible. So why don't we talk about like 3 degree of freedom joints? We just talk about 1. Yes. Yes. Remember minimum number of representation? So this ball joint is comprised, or when we are simulating it, of 3 R joints moved along different axes, X, Y, Z. Right? So that's how, so we will get there. Very good question, because you're actually thinking ahead of me. So we talk about the joint types as being prismatic and revolute, and everything else is built from this. Now, screwdriver is not a joint, but the motion of the screwdriver. So you only do rotation, right? What happens to the screwdriver head? Well, moves vertically, right? So we will model that. What is the other joint that with worm gear? Who works with worm gear? How does it work? It rotates, but because of the way that the pitch is machined, it actually moves longitudinal, right? So you can get a rotation and longitudinal motion of that. When you're modeling, it's going to be 2 things. Rotation and, so we are making things simple by introducing 2 concepts and then working with that. Right? Very good question. You will get there, you'll see we call it S-joint. All right, so this all was fun part from related to robotics. The second part is vector algebra, a little bit coordinate systems, still fun. So I put some fun in there. Why coordinates are very important. Why coordinate system? Why do we care? What are they? What are coordinate system first? And then why do we care about that? You are the someone that can talk. You're right here. I can ask you questions. Right. So again, critical thinking, we're thinking why we're doing all of this, right? Right.
Just to define where you are.
First, it defines where you are. Now, say if you were here and I'm talking to you, I say I'm in Scott. If I talk to anyone, I know how I say if I'm at Scott E40, they know where I am, right? Now, my sister lives in Vancouver. If I tell her I'm in Scott 040, what would she tell me? Right? It's like where's the Scott? If I talk to E.T., if he existed, like usually which planet are we talking about, right? So it's really important to have your coordinate system, to have a reference at what, with respect to what we are talking about position and velocity. Because remember, we are gonna talk about position and velocity for the rest of your life in fall in this class. So you need to have a reference frame. Every time you talk to me, you need to say that word. So everybody remember that, like, you're on a train, someone that on a train, and you're like outside watching the train. So that person thinks that it's going 20 miles per hour, you think it's going, I don't know, 40 miles per hour, right? So those are relative. It's also important you're measuring position and velocity with respect or relative to what frame. The frame could be on that robot or on that person. So we put one frame, reference frame, inertia on the center of the Earth, right? Because you're on planet Earth. So we took care of that one. You're on planet Earth. So if airplane goes up, so we consider Z up, right? So the airplane, if it goes up, everything is positive. On the water, what goes down, Z is negative. Sometimes you flip it over, but we know that the other two also change for simplicity. But the standard is right-hand rule. You put one there, we call it inertia. Then, depending on where you are, what is moving, you create different reference frames. Now, I'm gonna put one at the corner of that room and one where Michael is sitting. So if I go this way, Michael will report different X and Y, I'm not moving Z, right? Than the corner, which is my frame 0. So imagine there are 4 cameras at each corner of this room. We can use, we can create GPS network inside using camera vision, right? Because all 4 of them will read different positions and triangulate it and cover area. I think that's the technology you're using, because we're gaining, right? So that's what we could use one ground truth or one frame 0. So all the frames are known where they are with respect to that. So whatever they report, we know with respect to their position, and all of them we can calculate from the corner of the room. So we can calculate where I am from the corner of the room. Does that make sense? That's how basically it works. So if you have a robot that works inside a building, they don't have access to GPS. But either they have to use this camera system typing, like in most research labs, you have camera system, or they have to use other ways of pathfinding. So this is one way to know where you are, but it works with reference frame. That's why they're very important, and we put them in different places. But we always have one frame 0, frame 1, 2, 3, 4, 5, and 1 on the robot. So if my reference frame is, so there's one reference frame for me, if I move, what is my X, Y, and Z with respect to myself? Always 0, right? But I can tell my rotation also. So this one doesn't show anything. But I can know anything else with respect to me. So I need to have a reference frame. That's why they are very important. They will tell us where you are, where things are. So basically all of this that I just explained. As these all will be annotated, so you have that, you will have an annotated version. I added a few things. One thing that I want to show, so inertial frame, which is at rest and does not move, right? Because the center of the Earth. Now, the direction you see that the Z is pointing down, you need to check where, if you're reading a paper, reading someone's work, reading your textbook, check where is the direction of Z for the reference, for your frame 0 reference frame of inertia. Because you could show it this way, that Z is pointing down. Now, if Z is pointing down, which one of those is X, which one is Y? But call this closer to me, call that farther from me. Closer to me, X, right? Because point down, it has to go from X to Y. Now, if I draw this, which you will see, like we use the upward one. Now, which one X, which one Y? This way, right? So X, Y. So the direction of X, Y changes. So you can either use this or the whole figure. That's why when you're talking about the joints, we wanted to know where is the direction of Z, because once we know that, we know the other. We only show the X direction. Now you can have different kind of frames. We'll talk about it. Now, why we talk about why we don't use a non-inertial frame? Because they have non-zero acceleration. The acceleration of the planet Earth, like G, is fixed almost for our application everywhere, right? Does not, it's inertial frame. If you are in the space, then things are not inertial. They're different. So that's why the science, when you go to different space, then things are different. On planet Earth, you're all good with inertia. As far as I know, I don't know the future. All right, we talked about the space, which is position velocity. Your orientation could be your angular velocity. It also could be your your space or your position and your velocity. Now, if we have the x, y, z, then we have x dot, y dot, z dot, right? If we put the angle to orientation, we have theta 1, theta 2, theta 3, theta dot 1, theta dot 2. So I kind of talked about all of this. I'm just showing you what I mean. And this one is a good representation. So I actually want you to work on this. If I call this, let's see. I'm going to introduce position on X, Y, Z. Then this you'll see U, V, W. That's one way, or you can say X dot, Y dot, Z dot. But if you see U, V, W, that's the nomenclature for velocity. Angular position, you can say theta 1, theta 2, theta 3, or theta, phi, and psi, I think, or back the other way around. Theta, phi, and psi, I think. Then this one, P, Q, R. Why we went back to English instead of Latin, I don't know. Don't ask me. Now, if this is your frame 0, X0, Y0, Z0. And this one is frame B. This is ZB, then XB, YB. How do we identify the position of PQ? So P0 is a point in the space. So this is the corner of the room, right? This is a camera. I want to know where Michael's sitting. What's the position? What's Michael's position? What do I write here? What's the question you need to ask me? With respect to each one, right? Because there will be two different numbers. Remember, I said if I walk, this gives me a different position. So the position of that point, you need to know with respect to that point. You're right. So this point will have X, Y, Z, and some orientation, right? Theta, phi, psi, let's say. Then I can say P0 showing with 0 frame, meaning that I'm looking at it with respect to frame 0, becomes X0, Y0, Z0, and theta 0, phi 0, and psi 0. Meaning that the rotations are all about these axes. Make sense? If I were with respect to this, I will get two different coordinates, but they are the same. Yes. For position, yes, but I'm showing the state. So I'm also looking at the orientation, because orientation is also state that because your state has to show all the degree of freedom, right? It has to represent that point. Because here, if I only said XYZ, and that was the corner of the room, you give me an XYZ. The XYZ of this orientation, this configuration, would be the same as this, because I didn't change XYZ, I just changed the rotation. All right, so we have to add probability, because we want to know how this is located in the previous section. Does that make sense? Yeah, we are representing this in the space. So it would be 3 position, 3 orientation. Now, if you want to talk about the velocity of that point, if it's moving, you have to also give me 6 of that. X dot, Y dot, Z dot, PQR. Yes, someone raised their hand. Yeah,
So you have a water bottle, there's, where, at what point,
I said the corner of that.
they're on the water bottle.
Oh,
Orientation,
okay, good question. Can someone answer that? It,
always in the middle.
the center, yes, because how do I, so look, well, how do I represent that? I represent the corner, right? So you're in thematic right now. So it doesn't, the object itself doesn't matter. So we always represent at some point, we put that in the center of the mass. So that way we can actually get rid of the center of mass without having a fall, because if we needed to add mass, we can just say that's the center, this is how much mass it has, and we can do all the other calculations without having to do it. And keep the question with answer. What time is it? Okay, we're almost getting there. You probably cannot do your quiz because I even haven't gotten there. All right. I'm gonna talk a little more and then let you go have fun on your first Friday. Let's see, should I start this? Yes, I'm gonna finish coordinate systems and then let you go. So you all are familiar with Cartesians, right? So planar Cartesian 2D, spatial Cartesian 3D. I read it right. Not special. So when we get to actually, probably next class, we can catch up. When you present points and then we have a robot, anything that you want to present, basically assume a cube, and then the corner of that is going to be where we are. Because this, so this is the space that I'm going to put my object in, and all the positive directions right now are encapsulated in this. But we have also the negative directions as well, right? So if you imagine, if all of these were X, Y, Z positive, so this is X positive, this is Y positive, but these two are parallel, so this one is also, you can read as Y. And then here, this one's Z positive, so I should probably use different colors to be smarter. I should be smarter than this. So this is, let's say, your Y, so this is also your Y, and this one is my Z. So this is also Z because they're parallel. So if I needed to know what is P is, I'm basically projecting it on the axis. Now, this is simple, you all know that. But soon we're gonna rotate the axis. So everything has to be rotated. So we only work orthogonal. So the Cartesian tells us the axes have 90 degree angle with each other. This 90 degree doesn't change. So if I always have problem here because I forget to bring my popsicle sticks. I don't even know what it's like. Can I borrow it? So imagine these are your axes, right? Z, X, Y, or Z, X, Y. I'm measuring, this is my point, and then I'm going to rotate my plane. And I still should be able to say what's the position and orientation of this, but you see that these are all fixed, they can change, so that's the beauty. You'll be able to measure that. So you will find the transformation between this string and all the others that are rotating, so you have a rotation matrix. And once you have your rotation matrix, doesn't matter how much it rotates, you can get the angles and tell me what's the position of this. So basically, we'll write a code, find the rotation matrix, get this, and then say how many degree you want to rotate, -15, okay, that's the position. So basically all of the. Now, these are the types of coding assignment you will get. So this course cannot be real time because we don't have robots, we don't have sensors to use data online real time to do something, but we do our best, kind of either offline set of data or solving simulating with hazard content. Or that's the closest we can get for you to have a meaningful experience in robotics. And a lot of the time, if you're especially in research labs, they do simulation. Then there's funded, government, and they actually buy the toys and work with them. All right, so, I'm gonna end here. You probably cannot do the quiz, so I'm just gonna do the quiz that will like the math for the year. Don't do it. So, what I'm talking is this one. You cannot do this.
So it's CD001, what is the passcode? I've never said that.
Well, you don't need to take it, so you don't need
No,
the
the
passcode.
00.
Oh, that doesn't have passcode.
Okay.
It's okay. Yeah. That I forgot to update. It doesn't have any passcode. Let me close that.